Hi, my name is Seth Olsen. I'm a PhD candidate in the physics department at Princeton University. And today I'm going to be talking about some work on the O3a LIGO-Virgo data that was done with Tejaswi Venumadov and Javier Roulette, who are now at UCSB, Jonathan Mushkin and Barak Sakai, who are now at the Weizmann Institute, and Matthias Saldriaga, my advisor, who's at the Institute for Advanced Study. And this is also based on some prior work from many of these authors, along with Liang Dai, who's now at UC Berkeley. This is using the IAS pipeline to reanalyze the gravitational wave data from the LIGO and now Virgo experiments as well. Although here we are just going to consider the LIGO Hanford and LIGO Livingston coincident data. So this is only data with significant signals in both of these detectors in the first half of the third observing run, O3a. And we are using the IAS pipeline with some new improvements in the detection statistic and template bank, as well as a new parameter estimation software to analyze the O3a data and find 10 new binary black hole mergers, in addition to the 44 that were found by the LIGO-Virgo collaboration, and also an independent analysis that produces the OGC catalogs. So now let's take a closer look at those new events, along with an 11th event, which had previously been detected in the GWTC2, but was reduced to a marginal candidate in the updated analysis. So we're bringing this one back into the catalog along with these 10 new events, where we see some interesting astrophysical scenarios. So just to describe briefly what we're looking for here, two regions of the mass spectrum for black holes we like to talk about are the upper mass gap and the lower mass gap. Now, the upper mass gap is predicted by stellar collapse models, which say that pulsational pair instability and pair instability in supernova prevent massive stars from collapsing to black holes in this mass range. This is between roughly 50 and 130 or 140 solar masses. So when we find black holes in this mass range, this may indicate some other sort of formation scenario, such as this being a higher generation black hole or the remnant of a previous merger. Then on the low end of the mass spectrum, there's the lower mass gap, which is less theoretically motivated and more an empirical observation, especially in the early X-ray binary observations, that we don't see many black holes between about 5 solar masses and then that maximum neutron star mass, which, depending on your equation of state, will range from about 2 to 2.5 solar masses. But as we've already seen with electromagnetic observations and the gravitational wave data observations in previous observing runs and in O3a, there are black holes in this mass range. And here, like the upper mass gap, which also we've found prior detections in this range, we're just adding to this early view of the population to help get better constraints on some of these models. And now moving from the mass to the spin dimension, we're going to consider this effective spin parameter, which is the mass-weighted sum of the angular momentum projections onto the orbital angular momentum of the black hole spins. So the black hole spin components that are aligned with the orbital angular momentum, we're just going to sum these weighted by their masses. And this will give us a dimensionless spin parameter, which is the best measured in the data. And this can be made a little more rigorous with the Fisher information when we talk about the likelihood. But essentially, this is a good data analysis parameter. So we use priors that are uniform in this effective spin parameter and in the detector frame constituent masses. Now, with this prior, we find a number of positive and negative effective spin systems, both in the upper and lower mass gap. And in the lower mass gap, we also find a couple systems which may even have a neutron star based on their mass posterior overlapping the neutron star range. But we want to note that these are subject to these priors, which when you reweight, this can change the story both qualitatively and quantitatively in some cases. In others, they are very robust results to a number of reasonable astrophysical priors. So there is, for instance, at least one system, this 190910, which has a confidently negative effective spin regardless of the astrophysical prior under the reasonable range, which allows for all spins, even if it heavily suppresses them, such as the isotropic spin prior, which is used in the LVC analysis. Now, even under this prior, which is believed to describe the kind of dynamical formation channels where spins are randomly oriented that might result in one of these negative effective spin systems, this is still going to be showing us a primary black hole who's spinning around its own axis in the opposite direction to the orbital angular momentum. So this is the first time we've seen a system like this, and this is astrophysically interesting because of the formation channel it suggests and may have an effect on the inferred population distribution of the spins. So this, like these other new events, are going to be very interesting to look at under a number of different spin and mass priors, and may also have, in these cases where there might be a neutron star, some sort of electromagnetic counterpart signal. Under the right circumstances, these can be observable, although it would take some luck to have a catalog observation at the right sky location and time from an existing telescope. So we can look back on that with the posterior samples here, which are publicly available on a GitHub that's linked a couple of times in the paper. And if anybody wants help or has trouble getting access to those or needs additional information about the samples or the analysis that we did here and the triggering, please feel free to email me. I'm happy to work with anybody on making these results more portable. And one final thing about this population before I move on to how we get these with the pipeline is we also are now seeing a number of very distant events at high redshift, which is interesting because it allows us to look further into the cosmological history, which is one of the big advantages of this new era of gravitational wave astronomy. So moving on now, just briefly, and in the remaining time, I'll talk about the stages of the pipeline. So this end-to-end pipeline, we start with data from the LIGO and Virgo experiments, which is already calibrated and noise subtracted. So it's prepared in some sense, but we still consider this the raw data because it has to undergo our own signal processing stage where we add some glitch cleaning and notching of the loud frequencies. And also we estimate the PSD and do a drift correction for the leading order violation of the stationary noise assumption. And then we use a template bank that uses geometric coordinates to optimally place templates. And we get signal to noise triggers with this match filter statistic that will give us an optimal sort of 0th order approximation where we can choose candidates to be scored on this more computationally demanding statistic that now in this updated O3a analysis incorporates coherently multiple detector information. So we use this as a ranking statistic, which we can also apply to a background distribution that we estimate with time slides. And when we have these candidates, we rank them and make some cutoff. Here, just based on the literature, we use an astrophysical probability of 1/2 as the cutoff, and then we do some parameter inference on those events, which we will use this Cogwheel software, which is going to be in an upcoming publication by these authors, led by and largely thanks to Javier Roulette, who has worked also really hard on finding some interesting coordinates that allow us to have better sampling in more efficient and reliable convergence with Monte Carlo samplers. So this is based on some intuition from the post-Newtonian expansion, also employing the old methods from the existing IIS pipeline. We get these detections, and I'll just run through this really quickly. The PSD drift correction is just going to be correct so that the noise looks more like the kind of chi-squared distribution with the right number of degrees of freedom instead of this really heavy-tailed distribution where it's harder to get signals out. So this gives us a little bit more sensitivity. And we also gain some sensitivity in losing less near the edges of these bad data segments by making, with this in-painting filter, as it's called, the data insensitive to these noise, the test statistic insensitive to these data regions here where we have effectively zeroed the blue data, or the data after the inverse covariance has also been applied. So this is described in this publication, and we also then use this data with a geometric template bank that was described here, where we use a mismatch as the metric for our coordinate space and lay these geometrically uniform templates so that we get an optimal number of templates for the coverage that we want, and we can locally refine to get better coverage or higher effectualness. And here in O3a, we're also adding this sixth template bank, which is called VVH5, in addition to the existing 0 through 4 that we had in the O2 analysis. And so with this template bank, we're also going to apply some template prior, which will just correct for the fact that if we go uniform in these geometric template coordinates, then we'll end up overemphasizing regions where there's significant steep changes in the waveform morphology, but this doesn't correspond to such large regions of physical phase space volume. So we just correct this back to an easily reweightable and more close to physical distribution, like in the parameter estimation, which is flat in the effective spins and the detector frame constituent masses. And this allows us to not be overemphasizing these regions of parameter space where there are not a lot of physical templates. And so then with these templates, we use the coherence score estimation method that's described in the appendix D of the paper. And finally, we have the Cogwheel software, which will soon be publicly available. And we hope that everyone will check this out. It employs the relative binning or heterodyning likelihood method that now can efficiently evaluate higher multipole mode waveforms. And we use a processing waveform model as well, the IMR Phenom XPHM, and Javier Roulette's sampling coordinates, which will be in a paper released soon. And we efficiently evaluate these likelihoods and sample these parameter spaces so that we can get posterior distributions efficiently and accurately. And we encourage everybody to check this out, and please reach out to us if you have any trouble or want to know more about this. So thanks so much for listening.